Okay, guys, welcome back to the Wireless channel. Today we have the pleasure of having a group of colleagues from Brazil who talk about a very interesting waveform that we developed together called Affine filter bank modulation. So yeah, without any further ado, let's hear from Henrique. Henrique, take us take us away.
Okay, hello, my name is Henrique, and I will be presenting our ongoing research for a new waveform for high mobility environments called Affine Filter Bank Modulation, or AFBM. This work is being done in collaboration between us of the Universidade Tecnológica Federal do Paraná in Brazil, Constructor University in Germany, and Senan in France. Um, okay, first giving some context to this work. As some emerging communication applications like vehicle-to-vehicle, drones, and high-speed trains communications operate on high mobility scenarios, where Doppler shifts and multipath delays are quite significant. So traditional waveforms like FDM that is used everywhere these days, under doublet specific conditions, suffer from loss of orthogonality, leading to poor equalization and poor performance, making them unfit for this kind of application. And that motivated a lot of people to find new waveforms like OTFS and more recently AFTM, which is the foundation for the waveform that we will present now. Oops. Okay, but first I'm gonna give a brief overview about AFDM. It stands for Affine Frequency Division Multiplexing, and it's basically a modulation that uses a Sharp-based subcarrier mapping that maps data symbols into a discrete affine Fourier domain, and that's done through the use of the discrete affine Fourier transform, usually called the DAFT, instead of the traditional discrete Fourier transform used in OFT. In equation 1, we have the mathematical the equation I thought formulates the AFT, and we can see it's mostly the traditional DFT, but with two added terms. First, we have a Sharp in time, that is basically a Sharp that's applied to the original signal based on a parameter C1, and then you have a Sharp in frequency based on a parameter C2. When we refer lately about the DFT or EDAFT, we are talking about this expression. Okay, why this is relevant is because the key benefit of the AFDM is that it can achieve full diversity in doublet dispersive channels, making it a very good candidate for those novel applications. But it also inherits some of the same limitations as OFDM. These limitations being, just like in OFDM, AFDM has a high peak to average power ratios and a high out-of-band emissions. Also, the use of Sharps leads to poor spectral containment because the Sharps frequency tends to spread the frequency all around the bandwidth of the signal. And based on these issues, we looked into other techniques such as using a filter bank multicarrier or FBMC that can reduce the out-of-band emissions through subcarrier filtering and adapt spreading precoding that can reduce the peak to average power ratio. Um, and this brings us to our proposed solution, that is the affine filter bank modulation, or FBM, that combine both the AFDM and FBMC with the DAFT precoding. Why? Because it retains the robustness to doublet dispersive channels from AFDM, while also introducing filter bank processing, which ensures a low out-of-band emissions. And we also include a DFT-based precoding, which helps significantly to reduce the peak to average power ratio. It also adds more flexibility because we can choose different filters in case of the FBMC, and we can choose different stunning parameters that would be the C1 and C2 that I showed, or the FT in the previous slides, to adapt to different use cases and scenarios. Okay, so now I'm gonna give a brief overview of our scheme, the chain of modulation of our scheme. All of our implementation is made through matrix, so these illustrations help a lot to see each step. First, we have the precoding stage with KFBM symbols, each contains L over 2 KAM symbols that are mapped in the center of elements of a matrix A. Next, we have a diagonal scaling matrix JAG-B. It's mostly a implementation detail, but the purpose of this matrix is to scale the power so that the subcarriers powers are normalized after the filtering stage that will be applied later. And we have the WL matrix that corresponds to a DAFT matrix that spreads the symbol using the DAFT transform. This is similar to the DAFT spread used with FDM, but in this case we have more flexibility to do it the DAFT sharp parameters. And with this, the final spread output, the matrix X, is obtained by multiplying this matrix together. And this gives us the precoded signal that's read, that is going to be used on the next stage of our transmitter. Here we have the multiplexing stage. Based on X from previous stages, we apply the EDAFT in the transmitters, which works it's equivalent to the modulation AFDM. In this case, the EFDM would start aquí, the traditional AFDM. And since we want to be able to contain the frequency from the EDAFT chirps can spread, the size of frequency of spread P must be smaller than the filter bank size N. So a frequency domain zero padding is adding. This way, the frequency chirp is limited by the value of P instead of N. So that's what's described in equation 2 and 3. Equation 2, we have the padding, and equation 3, we have the final product in this case for this whole chain. Once the signal has been precoded and multiplexed, we go to the filtering stage, where the serialized signals then pass through the matrix, the filter bank matrix G. This matrix is a block Toeplitz matrix that corresponds to the impulse response of our chosen prototype filter. This matrix, in this case, is constructed based on the filter of choice, like Phidias or Hermite, and it applies a filter per subcarrier, not a filter on the entire signal. So the result obtained here is very similar to FBMC. Then the result is serialized and filtered through the filter G, and the output of this process is the time domain transmit signal S. That is the final CS signal that is sent over the wireless channel. So, in summary, our scheme can be either be seen as a finely precoded filter bank scheme, that is, adding the DAFT under the precoding stage to a filter bank scheme, the FBMC, or it can be seen as an AFDM scheme that replaces the usual sync sharp subcarriers that the rectangular window usually used in AFDM with a sharp filtered one. Okay, based on the transmission chain that I just described in a few slides ago, we can get to the effective channel being as the modulation under the modulation in this case, where H is the impulse response matrix of a double dispersive channel, and And we can see, looking at the effective channel, we can see that it spreads each symbols across the full time frequency domain, which allows to low complexity equalization delay Doppler domain due to the dense matrix coefficients that I'm going to show here. Here we have the results of simulations of the effective channel of our scheme in this case, and we can see that the three paths are spread apart from those effective channels. And we can see that the coefficients are very densely distributed, allowing the implementation of low complex equalization schemes. Now we are going to show a few results of simulations we obtained. The parameters used are the ones listed on screen. We simulated with an intermediate value of P, and as shown in the image before, the channel had three distinct paths. We simulate both with the Fidesz filters with a 4 symbols overlap, and the Hermite filter with an overlap of 1.5 symbols. Here we have the results of the PAPR, where the y-axis represents the probability that the PAPR exceeds a certain value of the x-axis in the B. And as we can see, at 10 to minus 4 probability, AFBM has a most 3 dB advantage when compared with the pure FDM. And here we have the comparison of the out-of-band emissions of AFDM and AFBM with both filters. We can see here that in particular with Fidesz filters, we can achieve an out-of-band emission as low as minus 100 dB. This is a big improvement over AFDM and demonstrates the effectiveness of the filter bank in containing the signal within an allocated bandwidth. Just a comment, a detail why the Fidesz is so much better than the Hermite is the fact that the Fidesz is designed to be a filter to be optimal in frequency localization, not so good in time localization, while the Hermite is a filter that's more balanced. It's as good as in frequency as it is in time localization. So depending on the scenario, we can choose different filters based on the characteristics that we are expecting. And that would be a brief overview of our FBM scheme. Our simulation shows promising results with improved both PAPR, that would be peak to average power ratios, and out-of-band emissions compared to FDM. And going on, we plan to develop advanced detection structures for FBM to further improve its performance and reduce equalization complexity. We are also working on the application of FBM for integrated sensing and communication, or ISAC. And we are also studying how the choice of the DFT parameters affect the signal characteristics and how they can be optimized. We have so far seen that the choose of the parameters, especially the frequency sharp C2, has a big effect on the PAPR. So we have to study further. And also for future implementations, there is still work to be done with the channel estimation itself. And that would be it. Thank you for your attention. And any questions, feel free to ask.
Thank you very much, Henrique. Guys, questions? Eddie?
I mean, I also have no questions, but maybe we could do you have any questions?
Okay, then let me give it a shot. Can you go just to the last page where you talked about some future directions? So about the chirp parameter optimization, in my understanding, one main problem here is that depending on, I mean, there are so many different optimization criteria, right? For example, you showed results in terms of PAPR reduction advantage. You showed results in terms of our band emission advantage and things like that. So my question is, do you think that it's possible to optimize all of them at the same time, or what do you see in terms of trade-off amongst these different criteria? There are others, of course, PER, etc., etc.
Yeah, from what is known, the sheriff parameter C1 has a quite specific restriction, specific constraints to be considered to guarantee a full diversity on a doublet specific channel. But about the parameter C2, there's very little literature about this. So we think that we don't know. We have to investigate it further, but we believe that yes, it's possible to choose these parameters in a way that it's possible to increase both PAPR and BER, for example, without any trade back, but we are not sure so far.
Okay, thank you. Anybody else? Any other question?
No, I'm good. Thank you, Henrique, for this very informative and interesting presentation.
Okay, if there are no questions, then I thank you very much again, Henrique, and we'll see you next time at the wireless channel.
Thanks, everyone.
Thank you.